In this video, we will be covering week 5 material from Statics 202, where we'll be talking about pin and support reactions and how they affect different rigid bodies. And in this video, we're mainly just going to be focusing on 2D problems. So, what is a pin and support reaction? So, this is the total external forces that are developed by gravity's influence and rigid body geometry. So if you think about Newton's third law, every action has an equal and opposite reaction. Right, and if it weren't for this law, everything would just be floating around. So gravity's influence, so say if you had just a surface here, gravity's influence acts down, but at a same magnitude, there's also reaction that acts upwards to keep whatever that is in place. So say if you wanted to keep just like a block in place, you would also need the reaction to the gravity in order to keep that box in place. So that's what we're going to be talking about. We're going to be talking about those reactions from that action of gravity and the weight of our rigid bodies. So we're going to talk about where our reactions are developed. So if support restricts translation in a direction, support reaction is developed. And this will make sense when I explain it using the visual diagrams in the next slide. So there are 10 main kinds of support reactions. The main ones that you will see, or the ones that you will see most often, are just pins that look like this. So these are the ones I see most frequently. Rollers, rockers, and fixed beams. Yeah, so this is smooth pin or hinge. So this is the one I was talking about here. So this one is seen quite often. I see rollers quite often, rockers, and fixed support. So these ones are probably going to appear the most, so you want to keep your eye on them. So other than these few here, the rest of the, I guess, different kinds of connections only have one reaction, and that would be our normal force, or a force of tension. So in this first one, you can see that with a cable, our force is directed just along the cable at whatever angle we need. So it's going to follow it and treat it as if it were in tension. Right? We treat all cables in tension. Okay, if you have a weightless link, so that looks like a pin with a link attached to our body, then this can be either in tension or in compression, but there's just one force acting along the link in either way. I can use red to make it easier to see. Okay, so if you have a roller, your force is going to act as a normal force, so normal to the plane it's acting on. So say normal to plane. Right, and in this case, because we're on a slope, we want to make sure that our force is acting perpendicularly. All right? Okay, same thing goes for a rocker, also a normal force to the plane. And for our smooth contacting surface, same story. Okay, so now if we have a roller or a pin that's in a smooth slot, it's the same thing, but it doesn't necessarily have to be acting upwards into it. It can be acting downwards. There's still only one, so it can be either direction. Holding it in place. Same thing goes for the member pin. It can be in either direction, as long as it is perpendicular to this surface. Right, and then we have a smooth pin or hinge. So here is a good example for me to explain what I mean by restricting translation. So if you have a beam that's attached to this hinge, you could still pick this part up, and since it's like a hinge, you could rotate it this way by picking up this end to make it look like this. Right? So that means you can move it around like that, but you can't move like the object itself up from where it's attached. You can't move it up. And you can't pick it up and slide it around, right? So you can imagine this hinge is fixed, like drilled into a piece of plywood, for example. And even though you can move like the rigid body like around in it, you can't actually pick up and translate it in the Y or the X direction. So because you can't move it in the X direction or the Y direction, that's why you develop two reactions. So you'll develop two unknowns, and they're not necessarily, let's see. Yeah, sorry. You might find that the direction of them may be different. So as we go through some questions, we'll see that directions can be flipped. But smooth pins, you'll see a lot. So those have two unknowns, right? So everything else we've covered up until this one has had one reaction. If you have a member fixed connected to a collar on a smooth rod, you will have a moment. So if it prevents rotation in a certain direction, that will cause a moment. And because you can't translate it upwards along this way because it's being fixed by that rod, then that means we develop a reaction that's normal to it, right? Because we can't pick this part up and move it upwards, right? Because it's fixed with that rod. Okay, and finally, if we have a fixed support, this is the only one that has three unknowns. So fixed support, since you can't move it, so if you had, I guess like a coat hook fixed to your wall, you can't move it and slide it up higher in the wall. You can't slide it to the right of your wall, and you can't rotate it, right? At least if it's secured properly. So because you can't translate it outwards, upwards, or rotate it, that rotation is also going to cause a moment, right? Because we're restricting movement in our radial directions. So fixed support is going to have three reactions: smooth pin and the member smooth rod collar member have more than one reaction, right? Other than that, we mainly have tension reactions or normal reactions. So now I'm going to introduce you to drawing free body diagrams with this example. So when I draw this, I'm only going to draw up until this point here because we have some reactions from there. So I'm going to split it into two, and you'll see why. So we're going to start So this is A to C. Right, and we'll draw some pre-existing forces in white. So we're given 2.5 kilonewtons at 60 degrees. So we want to include some important geometry. So if there's angles, definitely a good idea to include them. We have a moment of 4 kilonewtons per meter, times meter. Right, and that's all we know so far about what we have. So here we have a smooth collar, and we know this develops a normal force to the plane it acts on. So there is one that makes a 45-degree angle, and we have a rocker B here, so that's going to produce a normal force. And because we have this little pin here at C, that creates CY and CX reactions. And I'm going to call this normal A and normal force B. So that is our first free body diagram. So what we want to do, we want to isolate any components. We want to include our knowns and add reactions. So specifically when you have Y and X reactions, just going to assume direction. And when we solve for them in the next questions, you'll see that you can change the direction based on the sign of the values that you obtain. Okay, and so this is member AC. And if we drew CD, our pin here, we know that our pin develops a Y and an X direction. So this is DX, DY, we're assuming direction. And you'll see this again in later chapters, but I'm just going to kind of gloss over it. So if we already established, so because this little pin here at our C is shared with two members, so it's shared by our AC and our CD member, and we already assigned directions, then we are going to make sure those directions are opposite on our other member. So if we had positive X direction on our first member, on our second one, it's going to be pointing in the negative X direction and negative Y direction, which is opposite of our upwards direction for that pin. So that's kind of just a brief introduction. It will be making more sense later. So now we're going to talk about two force members. So if you consider this system here, if we were to draw out the two sections, so let's isolate this beam and this rod here in green. So I'm going to draw the beam in red. So if we had our first beam, so we have AX, AY from our hinge, and we have 4 kilonewtons of downward force. Now if I were to draw this connecting rod, we have pin reactions at both sides. So this is CX, CY, and then we have in our opposite direction DX and DY. So we have too many unknowns here, so I forgot to detail this. but we can go through it now. So when solving unknowns, we have three equations we can use. So we can solve for our sum of x, sum of y forces, as well as the sum of our moments about a certain point. So let's just say A for now. So you can only have three unknowns. So it's also a good indicator if you need to simplify. And in this case, we should listen to that rule because without our simplification right now, we have AX, we've got 1, 2 AY, 3, 4, 5, 6. And right now we have 6 unknowns. But for a second, I'd like you to imagine these as the X and Y components of a force that looks like this and that looks like this. So instead of saying we have our dx and dy, cy and cx, this is what we call a two-force member. So two force members are defined by having equal and opposite x and y reactions. So the magnitude of each reaction is the same magnitude, right? So dx and cx would match up, cy and dy would match up, but they are pointing in opposite directions, so that therefore we can simplify it down to these white forces here. So in this case, we are considering tension. So because we're considering tension here, when we attach it to our body, our red beam here, then we have to flip it and assume compression. So assume that the beam is now under compression, right? So if we were to add this force now here, so let's simplify this. So we said our two-force member is now in tension on its own member. That means it's going to be under compression when we combine it all together. So then when we put it all together, it looks like this, and we can just call this FBC. FCD. So that's how you can identify two force members. If there's too many unknowns, then that should be your clue to simplify, and make sure that the directions you're assuming go well with it. Again, we can determine the real direction of the reactions once we actually solve for numerical values, and we can use the sign that it produces to show what direction it truly is. Right? So we're just assuming in this case. So then once we make that simplification, now we only have three unknowns. We have FCD, AY, AX. So now we're golden. We're okay now. So let's actually put this problem to use. Let's solve it. So we have our AX reaction here. We have AY reaction, 4 kilonewtons. And now we assumed it was the rod is under compression, which produces a tension force. And this is FCD. And this is at an angle of 45 degrees, right? Because we have even sides in our X and Y direction. So this is 45 degrees. And this acts at 1.5 meters. Okay. So first step to solving this, we know we have three equations. So everything must be in equilibrium, which means our sum of fx reactions is equal to 0. sum of Fy reactions are equal to 0, and our sum of moments around a certain point are equal to 0. So we're going to use these three equations to solve for our three unknowns. So we're going to start with our x directions. So our sum of our Fx forces is equal to 0, which is equal to, and now we only have we have two x direction forces. So we have Ax in our positive x direction, so we're going to have a positive coefficient in front of it. And if we were to break down our FCD, it would have a negative x component and a negative y component. So that's where we do negative FCD, and this would be cos 45. Okay, so we're just going to keep it in that form, and we're going to solve afterwards once it starts coming together. Our Fy is equal to, so we have our positive Ay force pointing upwards. We established that our y component for FCD is pointing downwards, so that's negative, CD sine 45. And we have our external force of 4 kilonewtons downwards. Okay, so that's it for our Fy reactions. And now for our moment. So where should we put our moment? So we should put our moment where there are the most reactions. Right, because we know that moment is developed by our force times our distance, right? So if you have forces acting on the point that you're measuring your moment from, that makes your distance equal to 0. So let's look at our diagram and see which one would be the best fit for us. So in this case, I would be inclined to choose point A over here because we have two reaction forces going through that same point. So because of that, because we're measuring at point A, both Ax and Ay are going to be rendered as not contributing to that moment because they are going through that point exactly. So that eliminates our need to consider Ax and Ay, and so we'd instead consider our FCD instead, and our external force. So let's start with our external force. So we have 4 kilonewtons times our distance, which is 3 meters, and this is going clockwise, so then that would make it negative. If we're measuring at A, and FCD, let's break it into its components. So our x component is acting along the beams. That means it'd go through our point. So we don't consider our x reaction, but we can still consider our y reaction. So then that's FCD sine 45. And our distance is 1.5 meters from A. And this is a clockwise direction. Right, so we have all of our components here, and now we can solve for things on their own. So let's solve. Sorry, let me just erase some of this. So let's solve for our FCD first, right? Because we only have one variable in our moment equation, so that makes it a lot easier. So this makes it 12 equals negative FCD sine 45, 1.5. Right, and then if we divide that over, so you have sine 45 times 1.5, and 12 divided by this becomes negative 11.313 equals FCD. So what does this negative symbol mean? So this negative symbol means that the direction first assumed is wrong. So our FCD reaction, we drew it to be pointing away from our beam. But now after we've done the math to solve for it, we see that it's a negative quantity. So that means instead it'd be directed this way if we were to amend it. So we're going to redraw our diagram afterwards so you can see what that would look like. Okay, and now we can use this to solve for AX and AY. So let's solve AX. And this is equal to AX equals FCD cos 45. It's also going to produce a negative value of, this is times cos 45, and this becomes negative 8. So that means our direction for AX changes. And if we solve AY, AY is equal to FCD sine 45 plus 4. So sine 45 plus 4, and this gives AY is equal to negative 4 newtons, kilonewtons. Okay, so we've solved for all of our values here, and we see that they're all negative. So the directions that we initially assumed are not correct. Sorry, I'm running out of room here. So if we were to redraw this, now knowing our correct directions, 4 can stay the same. So AY we initially assumed was upward, but now that it's negative, we know it is in a downward direction with a magnitude of 4. We know our x acts in the negative x direction now at 8 kilonewtons. And we know that our FCD now acts towards the beam with 11.313 kilonewtons. You could still maintain the other directions and then just write the negative value, whatever you find easiest to keep track of, right? But if we were just to write it with our magnitudes and our correct directions, it would look like this. Okay, so moving on to our next example. Okay, so this next diagram, we want to draw the reactions and forces that are acting on this point here. Okay, so the articulated crane has a boom. Crane boom has a weight of 125 newtons at G. So this is our center of gravity. So we know that this has weight, and our weight acts downwards. This is 125 newtons at our center of gravity, which for a rectangular beam would be its geometric center. And if it supports a load of 600 newtons, so that's what this load is here, this is our 600 newtons, determine the force acting at pin A and the force in the hydraulic cylinder BC. So if there's a pin and a hinge, the diagonal, this looks a lot like our last question, so this is 2-force member. And we also have AY and AX development. So I'm going to draw a cleaner version of this so you can see what I mean. So if we just take a look at point A all the way down to our load. So I kind of sped through the 2-force member, but I can explain it in more detail. So say we had these two reactions, then we can assume it looks like that. So if we put the rod under tension, then that means it's going to look like it's under compression when we draw it from our beam. And this is at an angle of 40 degrees to the horizontal. Okay. So now at point A, we have an AY, because it's a pin, and an AX. The center of our gravity, we have a weight of 125 newtons, and we have our load of 600 newtons. So this is what our diagram looks like, and this makes sense that this is a two-force member, because without it, we would have more than 3 unknowns. So we have 3 unknowns and 3 equations, so yes, we can solve this. So let's start with our x forces. And this gives us our AX. If we break down our FBC components, we see that this is in the negative direction for our x direction. So it's negative FBC cos 40. Right, and then we have FY sum. So we're going to start with a y in our positive direction. FBC has a negative y component. So that's minus FBC sine 40. And we have our loads and gravity. So this is 125 newtons and minus 600 newtons. Okay, and lastly, we have our moment. So we learned that we want to have our moment wherever there is a point that has multiple forces acting through it. And for us, this is clearly point A. So that renders these two guys as not contributing to that equation. So instead, we have 125. So actually, no, I'm going to start with our on the right side. So we have 600 newtons, and this is at a distance of, so because it's a vertical force, we want to have a horizontal distance of separation between them. So I'm just going to clear this up so I can illustrate dimensions, right? So a downward force, you want to find the horizontal distance it takes for it to be in line with our point A. So it's 8 meters to point B, and that's another 1 meter to point A. So this is a total of 9 meters in our horizontal distance. And if we draw to go to point A, this is a clockwise moment. Now if we look at our gravity, so this acts halfway on our, this acts at a distance of 4 meters horizontal because it's a vertical force, so we want horizontal distance, and it takes 4 meters to be in line with A, and this is also in a clockwise direction, so this is 125 at a distance of 4 meters. And now we're going to use our FBC. So we can actually use both of our components because neither of them are in, so the lines of action are not in line with our point A yet. So if we took our x direction, so this is negative FBC cos 40, and this is times. So if we have a horizontal force, we want to find our vertical distance, and this is just 1 meter, as drawn above. And if we want our horizontal, sorry, I forgot to add direction. Also clockwise. All right, and we have our downward force of FBC sine 40. And this is at a horizontal distance of 1 meter as well. And we don't need to use our AX and AY because that is the point of our measurement. So let's start solving. So I'm going to solve on this side. So again, let's solve for our equation 3 first. So solve FBC, because in our moment equation, we only have one unknown, FBC. So if we move some stuff around, so we have 600 times 9 plus 125 times 4. So then this is 5,900 equals FBC. I'm going to factor this out. Cos 40 times 1 just makes it the same, plus sine 40. Okay, and if we move this around, then that gives, so 590 divided by cos 40 plus sine 40. And this will give us, and we move that negative sign over, this is negative 4,187.866 equals FBC. So the direction that we assumed is false. So it actually should be acting. So let's draw our kind of correct reprise diagram. So if we had it facing away, now that we know our direction, we know it is facing towards. And this was at 108.66 newtons. Okay, so now let's solve for AX using equation 1. So then we have AX is equal to FBC cos 40. So our negative answer times cos 40. And this is going to give us AX is equal to negative 3208.092. Right, and this is negative, so we need to put it into the opposite direction. So this has to go in our negative x direction now. Okay, so there is our AX, and now we can solve AY. AY is equal to FBC sine 40 plus 125 plus 600. And this will give us so times sine 40. And sorry, this is supposed to be negative. And we have plus 125 plus 600. And this gives us negative 9,966.908 in our opposite direction that we first assumed. So we first assumed it was going up, so now we know that it is going down. Okay, so that is how to solve that problem. So always make sure that you're checking for your directions, and you can always specify in your answer or redraw it. So another way to specify this is just to answer as our magnitude, and then just put a direction to show where it is. So then if I were to do this for AX, just state the magnitude and say that is going in this direction and this going down. Okay, so that is another example out of the way. All right, and we have this last example here. Okay, so let's start with our free body diagram for this structure. So start us off with this right here. Wow, that looks awful. Hold on. Okay, there we go, much better. So, very first thing, this was our first kind of reaction that we saw in our table. If I scroll up, right, this is tension from a cable right here. So let's start with that, and we can call this T, just for tension. We have what we already know. We have a external load 100 newtons at the end of our beam. We also have reactions at this pin, AY and AX, just assuming direction for now. And we also have a distributed load here. So I'm just going to do the math for that really quick. We know that our equivalent force acts at 1/3 of our length. So this spans over 4.5 meters and has a height of 200 newtons per meter, sorry. So we need the area of our triangle. So this is 200 times 4.5 divided by 2. This is equal to our magnitude of our equivalent force. This is 450 newtons. And if we take 4.5 and divide it by 3, it acts at 1.5. So 1.5, and we have our 450 newtons. Right, and I'll just draw some other geometry things. This is 3 meters. This is 4 meters. And we have an angle of 30 degrees. Okay, so let's start off with our equations. So we have AX in our positive direction. And from our tension force, our x component points in the negative x direction. So this is T, and this will be cos 30. Or y. So then this is, so our positive AY. Then our negative 450 newtons from our distributed load. The load of our end of our beam is negative 100. And the y component of our tension is upwards, that's plus T sine 30. For our moment, so which point do we want to select? I would select at A because it has the most things going through it. So we're going to set this about A. Okay, so some things we can eliminate. So our y component of our tension force runs through our A, so we're not going to use that. Okay, so let's start out with our tension in our x direction. So this is negative, actually no, sorry. This is T cos 30. And since it's a horizontal force, we want our vertical distance, which is 7 meters. And it would go in a clockwise direction to get to A. So that's our tension out of the way. Next we have this 450 right here. And since it's a vertical force, we want our horizontal distance to get to A. So this is 450, and we measure that to be 1.5 distance away from A. If we wanted to get to A, it would be in a clockwise direction. If we had our load, this is 100 newtons at a distance of 4.5 horizontal distance. This would also be going in a clockwise direction. And yeah, those are all of the forces that we use for our moment equation. We can solve for t right here. So I want to solve, so this is equal to t cos 30 times 7. And let's move our 450 and 100 over. So 450 times 1.5 plus 100 times 4.5. So this is 1,125 is equal to t cos 30 times 7. And if we move our cos 30 times 7, this gives t is equal to and now we have a positive number. So in our previous examples, we were getting negatives, but now that we have a positive, this means our assumed direction was correct. Okay, so now if we use this to solve our AX, this would be, so AX is equal to t cos 30, which is equal to 160. It's also a positive quantity, so our direction for AX is correct. And if we solve AY, so AY is equal to 450 plus 100 minus t sine 30. So 450 plus 100, then minus sine 30. This also gives a positive value of 457.212, and our direction assumed was correct. So if we added those directions, we just kind of show that our initial assumptions were correct. Right, and that is how to do that question. So that brings us to the end of the notes section of this week. Join us in the next video where we're going to solve some practice questions relating to the different reaction forces and how to use the sum of Fx, sum of Fy, and our moment equations to find the values of those quantities with some more 2D problems. I'll see you in the next video. Thanks for watching.